Radioactive decay. Radioactive substances decay by spontaneously emitting radiation. If mass of T is the mass remaining from an initial mass m0 of the substance after time t, then the relative decay rate is minus dm dt divided by m, has been found experimentally to be constant since dm dt is negative. The relative decay rate is positive. It follows that dm dt is equal to km, where k is negative constant. In other words, radioactive substances decay at a rate proportional to the remaining mass. This means that we use theorem 2 to show that the mass decay exponentially. So we now use this theorem to analyze this constant value, which is m0 exponential kt. Physicists express the rate of decay in terms of half-life. The time required for half of any given quantity to decay. So let's have an example. Example, the half-life of a radium-226 is 1,519 years. Examples of radium-226: Hertz mass 100 mg. Find a formula for the mass of the sample that remain after T years. The exact things you do here is, we understand that we want to get the, he said let m of t, he said, m of t of mass 226 that remain after t years. So there is a way we represent it. We said, you said the m dt is equal to km, and the initial mass, because it's a sample, the initial mass is 100. We can now rewrite it to have the mass as a particular time give us the mass at initial value at exponential kt. We now give us, we have been given the initial value to be 100, which is 100 exponential kt. But we still have to have one thing in our mindset, that the mass at 1,590 years, the mass of the sample given, the half-life of the mass of the sample given will be 1/2 times 100, which is equal to 50. So we can now bring out an equation to say that because the same mass is this, the mass of T can be, so we have 100 exponential kt is equal to 50. Let's deal about this equation. So because we are going to use these informations to get the value of k, that's constant. So we now solving this equation. Let's now solve it mathematically. We have 100 e exponential kt is equal to 50. Let's divide both sides by, let's divide both sides by 100. So we have 100 over 100 exponential kt give us 50 over 100. Exponential kt is equal to 1 over 2. So, if now I want to analyze a value of t now, because we need the value of k. Let's go back and see, as I've said earlier, that the mass, the half-life of radium-226 in it is 1,590. So it is this year that we are going to use to get exact value of k. Therefore, you said exponential k times 1,590, sorry. 1,590 is equal to 1 over 2. So it will give us exponential 1,590k is equal to 1 over 2. So now, you now say that 1,590k, this is a logarithm form. It will turn to ln half. So 1,590 will give us minus ln, but how does it look like? Said ln 2 raised to power minus 1. So and the logarithm of, so the logarithm, it will now give us this minus 1 will come down. It will have 1590 constant is equal to minus log 2. So what I mean by log 2, ln also means log. So now, the max of the time, we have used the mass at 1,590 now to get a, so the value of our constant will now be 1,590 constant will now be minus ln 2. You said divide both sides by 1,590. So 1,590k onto 1,590 is equal to minus ln 2 over 1,590. So this will cancel this. The value of our k will be minus ln 2 over 1,590. So this is the value of our k. So the constant is minus ln 2 minus ln 2 divided by 1,590. So we are able to generate a formula for the mass of any particular time now to give us 100 exponential. So instead of now writing a kt, this is our k. So we said minus ln 2, you put it like this, divide by 1,590. So, it is minus ln 2, both of them are numerator. So that is why minus ln 2 and t, they are numerator. It is only the 1,590 in is denominator. So now we are now able to reach the place to start solving. We are able to solve question A. So this is answer for question. This is how it's look. This is how it comes. This is our answer. So now, the question now say, what mass remaining after 1,000 years? Remember, the total years is 1,590. So we now want to know that what mass remaining after 1,000 years. So the only thing you do, just do here, where this T is, you just put 1,000. That is all, nothing to do. So let's say the B part. The B part said the mass remaining, after 1,000 years is, so you said mass at 1,000 years will now be, this is our answer, 100 exponential minus ln 2. You know there is a time here. You see the formula? The time here, you put 1,000 times 1,000 divided by, everything is under exponential, 1,590. So, in pressing much of your calculator, you have 100 exponential minus ln 2. You put the bracket. So, let's divide 100 and 100 divided by, let me do it. So, after you divide this will give you 0.63. So you now have 100 exponential minus 0.69 times 0.63, because the lane tool is 0.69, so we have 100 exponential. So let's multiply the two. 0.69 times 0.63. So we have minus 0.4367. So we now give you 100 times. So let's find the exponentials of minus. So we said, let's press it. We have the exponentials of minus 0.43, exponential of minus 0.4367. So therefore we have 0.646 milligrams. So by the time you multiply together, we have 64.6 milligrams. So approximately we have 65 milligrams. So that is how the workings come across. So we are able to solve the question B. So he said, the third question said that when will the mass, he said, C, he said, when will the mass be reduced to 30 milligrams? So in solving this, we only apply the formula to, like you said, solution. We have 100 exponential minus ln 2 times time divided by 1,590 90. This is 590. 1590 is equal to 30. So by the time you divide both sides by 100, we have exponential minus ln 2 t divided by 1590 is equal to 0.3. So now, by making e not to be there, we have minus ln 2 over 1590 is equal to ln 0.3. So we have t here. So now let's cross multiply, so we're able to get our answer. So it means 195, go and multiply this, we have minus ln 2t will be 159 1590 ln 0.3. So our t will now be minus 1590 ln 0.3 over ln 2. So you just press this in calculator. Let's do it. We have t is equal to minus 1590 times. So let's divide this. Let's press it and find the answer. Let me press calculator. You said ln 0.3 ln 0.3 is equal to, that is, we have minus 1.204 over, so let's find ln 2. Let's find ln 2 is equal to 0.69. 0.693. So by the time this minus multiply minus, automatically to give us plus. So let's multiply it together and get the answer. So we have, let's say that let's start so you'll be pressing it the way I'm pressing it also for you to get the correct answer. 1590 times 1.204. So everything we give you, it will be 1914.36 over 0.693. So I just have to approximate immediately. So divide by 0.6993. So we have 27. So for me to approximate it to the last answer, we have 2762 years. So this is the final answer. So for approximately, the real answer is 2762.42. So I approximate it to get this answer. So I have been able to solve what do you understand by radioactive decay, and this is how we're able to use the topic to analyze it, the population growth, to analyze the theorems of population growth, to analyze. Don't forget to subscribe to this channel as you are watching this video, also to share it to those that need it. Newton's laws of cooling. Newton's laws of cooling states that the rate of cooling of an object is proportional to the temperature difference between the object and its surroundings, provided that these differences is not too large. The law also applies to warming. If we let T of T be the temperatures of the object at time T, and Tx be the temperatures of the surroundings, then we can formulate Newton's laws of cooling as a differential equation, which lets us to know that the T with respect to the temperatures of the object, it will give you a constant of temperature differences. Where K it is a constant. This equation is not quite the same as equation 1. So we make the change of variable to be the y of t. And the t of t minus t of x, because t of x is constant, we have derivative of y, that means change in y. With respect to the times of the object, it will give you the temperatures of the object, and so the equation becomes dy dt is equal to ky. So let's have an example to explain these Newton's laws of cooling. How does it work? An example, under example 3, says that a bottle of iced tea at room temperature, it means we will be given a room temperature to be 72 degrees Celsius, is placed in the refrigerator where the temperature is 44 degrees. Please, before I proceed this question, let's read the question again. The bottle of iced tea at room temperature, telling us that the temperatures of the ice is 72 degrees Fahrenheit. Is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the tea has cooled to 61 degrees Fahrenheit. A. What is the temperatures of the tea after another half hours? B. How long does it take for the tea to cool to 50 degrees Celsius? Now, before we proceed, let's have some look of things that let's just put like let the T of T be the temperatures of the ice, temperature of the ice after T minutes and the T of X be the temperature, surrounding temperature, So, which is it has been given, which is our Tx is 44 degrees Fahrenheit. That is temperatures of the surroundings. But recall that the Newton law states that Newton law says that the T with specific times give us K onto T minus 44. So, but there is the temperature difference. This T minus 44 represents Y. So let me proceed to the solution. You know that the temperature difference, we call Y changes of the variable. We have temperatures. There's a changes will occur to the variable, but the Tx is 44, that is surrounding temperature, must be subtracting from the real temperature. So then we can now say that the initial values of variable changes will give us initial temperature minus 44. So if that should be the case, meaning that y0, that is initial value of the variable change, will now be the 72. That is the real temperatures of the ice minus temperatures of the surroundings, which will give us 28 degrees Fahrenheit. So why now satisfy this equation to say that dy dt is equal to ky, meaning that the initial value of y give us 28. So that is the initial, but according to the law that we have started proving, it let us to know that for a particular time, the differential equation for a particular time will give us the initial value of that y exponential the constant of the time. So that is for a differential equation formulated. So therefore, and we know that our initial value is 28, so making 28 EKT. That's just the equation for y of t. So y of t now give us 28 EKT. So now if y of t is 28 exponential kt. But recall from the questions, let's go back to the question, what he said. He said, after half an hour, the tea has cooled to 61 degrees Celsius. So, meaning that, he said, after half an hour means 30 minutes. So, he said the tea has now cooled to 61 degrees Celsius. So what are the terms common? Recall, he said after, this is T of 30 minutes. Now that is what I'm just trying to say. Half an hour. He said it has cooled. It means T of 30, now 61. But recall, we now need changes of variable. We now need the original temperature minus temperatures of the surroundings, which will give us 17. So, and you know that the change of variable, which is y30, and recall that y30 will also give you 28 exponential. So, instead of writing the time now, that is kt, you will now write k times 30, which will give you 28 exponential 30k. Can you see it? So therefore, let's now equate it together that y of 30 is also 17, y of 30 is also 28 exponential 30k is equal to 17. That's just the value. So let's start making to get the value of k. Divide both sides by 28. So we have 28 exponential 30k over 28 is equal to 17 over 28. So this will give us exponential 30k will give us, it now give us 17, it will remain 17 over 28. Now, how do we now get the value? Let's press calculator, and to know what 17 over it will give us. Let me press calculator to give us what we need. Let me press it. So we want to get the value of 17 divided by 28. Let me press calculator to get. So you also press it where you are. So 17 divided by 28. It gives us 0.607. So meaning that exponential 30k is equal to 0.607. So therefore, in view of that, what you do next is you now say that 30k is equal to ln 0.607. And what is the value of ln 0.607? So we also go to calculator again to press the value of ln 0.607 bracket close. So it gives us minus, so the value now gives us minus 0.4999. So after giving us 0.4999, so we now say that k is equal to minus 0.4999 over 30, which is equal to, so therefore, so let's also press calculator to divide it by 30. Said divide by 30. So we now have minus 0.01666. So we try to approximate it to have, let's put an approximation sign, 0.01663. So now, the original equation for the y of t now will now give us 28 exponential minus 0.0163t. So therefore, we are able to see the exact equation of the temperature change of y of t to give us 28 exponential minus 0.01663t. But recall, I started this equation from one thing. I said in variable changes, I said the temperature minus 44. The original temperature minus the temperatures of the surroundings. Now we are now want to use this value to now bring another very beautiful equation to say y of t will give us the t of t minus 44. Let's make the t of t to be the subject of the formula. We now have the t of small t will now be 44 plus y of t. And from this equation that we have improved, we are able to get the value of y of t. And the y of t is, so we have say t for a particular time, we have 44 plus, so y of t is 28 exponential. So we like to write 28 exponential minus 0.01663t. So that is t. But our questions still go further. In A, he said, let's go back to the question. He said, after half an hour, the t has equal to 61. These are the things that we use to deduce the formula. He now proceeds to say, what is the temperature of the t after another half hours? So for having another half hours is showing to us that for having another half hours, meaning that the t of 60, because you had 30 plus 30, will now give us 44 plus 28 exponential minus 0.01663. So the value of time will now give us 60. So the t of 60 of 1 hour and 30 minutes will now be 44 plus, so let's 28 times. So let's see the value of exponential. So let's press calculator to know what the value is before we proceed. So he said, let's see what it is. So used to also press calculator to get it clear and clear. 1663 times 60. So we have 0.099. So we have exponential minus 0.9978. So which will be 44 plus 28 bracket. So let's find the exponential functions of 0.9978. So I also press it, exponential minus raised to power minus 0.9978. So it gives us 0.36369. So the t of 60 now will now be 44 plus 28 times, we said, times 0.369 times 28. So it gives us 10.3. So give us 10.32. So by the time it's an approximation to this stage, so the value will give us 54. We approximate to is 54 the value, but since it's 53, 53, let me claim it. 53. Now, so the approximating value of 660 is 50. So now, so we still go for. Sorry, we can't approximate this now. Sorry, that is 53.2. Let's say 53. So if the T60 is 53, approximate to 53, so now we now have a question says that it said in the B part, how long does it take for the T to cool to 50 degree? So for the T to cool to 50 degree, how long does it take? So let's try to find it. The B part now. You know that the T of T now gives us to be 50, but we need to get the time. Plus 28 exponential minus 0.0166 T. So it's equal to 50. Since you have gotten the equation, the remaining one is simple. So you just say that 28 exponential minus 0.0166 663t is equal to 50 minus 44. So 28 exponential minus 0.01663t is equal to 6. So let's divide both sides by 28. We have exponential minus 0.01663t is equal to 6 over 28. And what is the value of 6 over 28? Let's press it in calculator. So we have 6 divided by 28. So we have 0.21. So the values give us 0.21. So for having 0.21, so we have exponential minus 0.01663t is equal to 0.21. So therefore, we said minus 0.01663t is equal to ln 0.21. So minus 0.01663t is equal to, so let's go and find the value of ln 0.21. Ln 0.21. So we have minus 1.6 minus 1.561. So our time will now be minus 1.561 over minus 0.01663. So let's divide the both. Firstly, the minus we cancel minus. So minus we cancel minus, divide by 0.01663. So 663. So the value will give us 93.8. We have a 93.85. So this is 93.85. So therefore, that is approximately to, let's put approximately to 94 minutes. 94 minutes. So, and we need the time. So let's write it in formal way. You said T cools to 50 degrees Celsius after 1 hour. So that is 60 minus 94. You see I have 34 minutes. So 1 hour 34 minutes. So that is for that. So this is, so thanks for watching for the beautiful class like this. Compound interest. Example 4. If $5,000 is invested at 2% interest, compounded annually, then after 1 year, the investment is worth $5,000 times 1.22, which will give us $5,100. After 2 years, it's worth 5,000 times 1.02 times 1.22, give us $5,200. After 2 years, it's worth $5,000 times 1.02 or raised to power t. In general, if an amount is 0 notes is invested at interest rates 0.02 in this example, then after 2 years, it was A naught 1 plus R raised to power T. Usually, interest is compounded more frequently, says n times per year. Then in each compounding period, the rate is R divided by n. That is the rate, that is, yes. And there are nt compound period in t years. So the values of the investment is A is equal to A naught, brackets opened, 1 plus R divided by n. So let's try to give a little analysis of what I've explained better. For instance, maybe after 3 years, after 3 years, for example, after 3 years, at 2% interest, a $5,000 investment will be worth so it will be in this form: $5,000 because it's 3 years to 1.02 or raised to power 3, which by the time you press in calculator, it will be 5306.04. So for 6 years, because the compounding interest for 6 years also 1.01 or raised to power 6 will give us in dollar 5307.60. But this is not exactly where I'm going to. You have given an interest rate with monthly compounding. Now, this is this one is annual compounding with annual. This is annually. This is 6 months is semi-annual. That is 6 months semi-annual. But now, we want to talk about but in overall, what exactly I want to explain here is this. The formula is for the amount of the compounding interest for we want to make the n to be infinity. That's where I'm going to. I want to end, so for infinity times of the year, we have limit n tend to infinity. For the principal to be 1 plus R over n all raised to power nt. So now that is the number times time, so rate times time. So and also I want to make my n to be n over R. Now, if my n is n over R, this nt, record that nt can be written as n over R times RT. If you agree, it can be written like this, nt, because by the time R cancel R, it will become to nt. So, and I want to rearrange the formula for the A of t, but as the n tends to infinity, at which is 1 plus rate over the numbers of months, or in yearly NR, or into RT. So I'm trying to rearrange the NT. Now, what I want to do is that A naught is equal to A of T will now be A naught. You bring it out to the limit of n tends to infinity, bracket open 1 plus R over n onto n divided by R, bracket close, RT. Now what I need from here is, I want to recall that I have said earlier here that m is equal to n over R. So, meaning that R over n will be 1 over m. So therefore, to give us A naught, limit n tends to infinity onto 1 plus 1 over m. The same thing applicable to it because we have n over R will be m, because m from here is n over R. Yeah, good. So that is why here is m, all raised to power RT. So just want you to know that because there is a constant, what I'm just trying to say, the limit in this expression is equal to the number of exponentials so with continuous compounding of interest at interest rate R, the amount after t years. So now the amount because it's where I'm going to is that for all my proving, I just want to write that the amount after t years is A of t exponential RT. This is what we are going to. So by the time we differentiate this A, you differentiate with respect to t, the R will come here because of exponential differentiation onto EA RT. So it will now be continuous variable, meaning that the A, the t will be RA of t. This is where I'm going to. So at the point that after 3 years, if I want to do, just say A of 3 will now be $5,000 exponential because it's constant. So we have given the rate to be 0.02 multiplied by 3, so to give us 5,309.8. So because so didn't waste much of your time, that is why we are able to approve the differential equation to this extent. So as you watch this video to the end, you try to subscribe to the channel and give us put it in notification anytime I'm releasing the video. So if you see what you are doing is good and you're able to gain, try to subscribe. So thanks.